So today's talk is about VS Code extensions and how we can use extensions. And we'll also see how some attackers have used extensions in the wild to essentially compromise a bunch of stuff and how we can make it better. Not to give any ideas to the ATPs, but let's get started with this. So before any of that, let me introduce myself. I'm DB. I am a malware developer with BHIS. Previously, I've been in consulting. I've been a researcher for the longest time. I'm also a cat dad, which is one of my more important roles. And when I'm not working, I'm just nerding out on a bunch of stuff. So if any of this is your jam, find me, hit me up, strike up a conversation, say hello. But that done, let's start with a little exercise, right? So in the next slide, I'll have two screenshots from Windsurf. One is a malicious extension, and one is your regular extension downloaded from the store. So can anyone tell which one of these will get a shell on your PC versus which one of these is the legitimate one? A bit difficult, right? You've got the download numbers, you've got this reviews and everything. Let's do one better. This is Windsurf. So just a preface. Live Preview is a Microsoft-published extension. So we might think that, OK, Windsurf is not a Microsoft product. Let's check it in VS Code. And if you hover over the little Microsoft blue tick, it says that, hey, this publisher is verified from Microsoft. But again, one of these, not telling which one, because honestly, I've forgotten as well. One of these will get a reverse shell on your PC. One of this is your regular install from your store. So hopefully by the end of this talk, we'll figure out how we can make this. But just so that we are all on the same page, who here hasn't heard of VS Code? Anyone? Pretty much everybody. I created the slides for this in VS Code. So it's pretty popular. But there are a couple of things which we need to know about VS Code. One is that it's an Electron application. Why is this important? Because whenever we talk, like in the last slides, we talked about running shellcode and stuff. And Electron sandbox imposes certain challenges when it comes to that. For example, ever since Electron 21, if I'm not wrong, the sandbox broke a lot of the FFI stuff which we previously had. So that's an important thing to keep in mind. Second thing is VS Code has a dedicated marketplace. The Microsoft Visual Marketplace for extensions, it's almost exclusive to VS Code and Codium. Thirdly, extensions. One of the reasons why VS Code has been such a good target is because you can expand the functionality of it, unlike a lot of other editors. I mean, you can also expand the functionality of Vim and stuff, but more developers are used to this. And another very important point is, when we are doing malware development, it's very important to stay on the low, right? So usually we try to avoid processes which are important. And VS Code does this thing where it delegates every task to a different process, not a new thread, like which you'd expect with like most software. It delegates a new process. So even if your malware does something sketchy or you bork the process, the developer who is actually using that, they won't feel the effects of it like to an extent, right? So why target VS Code, right? There are a couple of reasons. One, developers and stuff, they have a lot of API keys. They have some really sensitive information, access to prod environments. That's definitely one. Second thing is cross-platform. So if you're targeting developers on Mac, Linux, Windows, you have a dedicated way of attacking them. And finally, this is more Windows specific. The payloads are run by code.exe themselves, which is a Microsoft signed binary. And anybody who has been in the malware development space or in the EDR space knows that having a Microsoft signed binary run your shellcode or run your malicious stuff, it's one of the most efficient ways of bypassing certain EDR checks. And finally, this was a lesser-known attack vector when we started it, which was like 2 or 3 years back. Right now, more people, especially in the wild, have started using it, and we'll see some cases there. So this might just fly below the EDR. Another reason why this talk came up at this point is the rise of AI-powered IDEs, right? For the last couple of years, we have seen Windsurf, we have seen Cursor, more and more developers using these things to write code. Now, at the core of these products, it's still VS Code. They just forked it, slapped an AI on top of it, and like, hey, new product, new shiny toy. But when you fork VS Code, you also inherit its vulnerabilities, its shortcomings, and stuff like that. But there's another thing. With great AI editors come marketplaces which are not heavily monitored. Why do I say this? If you have used these code editors, you might be familiar with the OpenVSX marketplace. Now, Microsoft being Microsoft, they're like, hey, you can fork our product, you cannot use our store. That's us. You shoo, something like that. But so OpenVSX, they were like, you know what? We are going to create our own dedicated marketplace. Now, why is this important? Microsoft is a big organization. They have lots of money to burn. We have seen their investments in AI, so they have cash, right? So they can employ a lot of people, a lot of more technical stuff to monitor the marketplace. However, OpenVSX does not have as many resources as Microsoft. So often we'll see that malicious extensions, which are pushed on OpenVSX, they go unnoticed for the longest time. They rely a lot on community as well. So this is something which attackers have been using for delivering payloads. But we have been talking about extensions. So before I proceed, I just want to take a little while to explore what exactly an extension looks like beneath the hood. So the file format for extensions is VSIX, and it's a very fancy zip file. That's it. We have the OPC format, and what it does, it takes your code for the extension, zips it up, and it says, like, hey, this is a shiny new extension. So first we have, if you unzip an extension, you'll see these files. The first one is a content type XML, which is it maps the MIME types and stuff. Next is some metadata, which is used by VS Code. And this is finally, you'll see the actual contents which run the extension, right? So whenever you install an extension, these contents are unzipped, and they are stored in this particular folder under your home directory. This is for Linux and Mac. The same translates to Windows as well, under .vscode.extensions. And something to note here is, one, there is an extensions.json file. We'll come back to it later. And then you have all your extensions with their particular version numbers. They are unzipped and stored in there. Now, again, this extensions.json file is really important for us because it has a lot of information about, hey, where does this extension come from? Where is it stored? Or what kind of properties does it have? So we will return to this. But right now, let's look at some attacks in the wild, or like, why should we care about VS Code extensions? So these are just 3 attacks. There are plenty more. So I think these are my favorite 3. I have a favorite cyber attack at this point, been in the industry long enough. But the first one is a Solidity extension which stole 500K from a crypto developer. That's like too many Lego sets, or maybe one Millennium Falcon one, the dark one, if those of you know, they know. Second is a teen PCP in GitHub breach. I was traveling around having the time of my life 2 weeks back, and apparently God hates me. So they also used GitHub extension, so I got to cover that. And there's Glassworm. Glassworm does something really interesting, and that's a technique which we were using, so I think they stole my idea or something. But anyways, before we talk about the 500K stuff, it's very important I introduce this particular extension from a Solidity developer. This is a very popular extension, right? It has been on the marketplace for 10 years. It's used by anybody who's in the blockchain. It essentially helps you out with coding, right? So this is what the attackers used. This is the extension which they published. And we can see, if we go back 2 slides, how similar these two look. Now, yes, there are some visual differences, but think about it from this standpoint. So this is from Cursor and OpenVSX. What the attackers were able to do here is they were able to modify the like the search order in such a way that if you typed for Solidity, the malicious extension came first, then came the real one, right? And developers were like, okay, this might be the real one. This seems to be more popular. Install. let's take a look at the code. So if you take apart the extension code, this is how it looks. Anybody make sense? Neither can. Nope. But, if you zoom in at the very end, you see this particular thing. And anybody who has been in the malware space will be like, hey, wait a minute, PowerShell, Qtion, policy, bypass, that's malware 101. So if we throw this in a beautifier, make it look pretty, we see this is the code. So essentially, they were using VS Code to deliver a second stage payload. We'll not dive into the details of whatever happens after this, but this is what I wanted to point out. And you might think it's over, but no. There's another one, DJ Khaled. They published another extension where they used the oldest type of squatting trick in the book where I might be butchering the name, so apologies. So the actual extension's author's name is Juan Blanco with a small L. They used a capital I in there once. And they tried to balloon the number to 2 million downloads, but somehow that did not affect the search order. But you can see how similar they look when you're looking at them in Cursor AI. Right. So they were persistent. Now you might think that, okay, this is a one-time attack against using Solidity. There are another ones. So these are all the extensions which used a similar format, a similar naming scheme. Like we have this joke that, hey, here's a drinking game idea that if you have an extension which mentions Solidity or Juan Blanco, take a shot. And probably by the end of the list, you'll have a fun time. Don't try that. But now let's move on to something more recent. Let's move on to the GitHub breach. So it was a combination of two things. It was a supply chain attack plus a GitHub extension breach. So first, Team PCP, they launched a supply chain attack and got one of the tokens of the developers of the NX console GitHub extension. They pushed a commit, an orphaned commit to another repository, JavaScript-only. Then they did something. They pushed a version update to the VS Code extension. This is very important because VS Code has a feature called auto update. Whenever you push an extension, and if your auto update is on, it fetches it, it runs it up, it updates it. So 18.94 was all right. They pushed an update with the malicious payload in 18.95, and some GitHub developer had the extension installed. It pulled the update, and boom, bad stuff happened. That took a lot of time to animate. But anyways, just let's take a look for a while at the extension or like what it does for a bit. Again, they had they had a hash which they were checking. They were like, hey, if this hash does not match, can you create a task like install MCP extension, which is like a real task which you will expect from NX. But the thing is, if you look very carefully here, it was fetching the orphaned commit which they had previously pushed, and that had the next stage payload. Like, it's a big complicated graph, right? They do a lot of things. But the long and short is, for a very brief instant, GitHub became truly open source against their will. So again, we see VS Code being used to deliver malware. Now comes Glassworm. So Glassworm is a malware which had multiple campaigns, and we will cover two of them. The first one is where you can see him. So this is the malware source code. You see the big empty block in between? You might think that, hey, wait, that's empty. Where's the malware? That's just enter, enter, when your cat sleeps on your keyboard or something. But if Kung Fu Panda taught us one thing, it's never really empty. There are Unicode characters in there. Poe didn't know the Dragon's Skull had Unicode characters. It just couldn't render it. So this was published by the Koi research group, and they said that this whole chunk, they have Unicode characters which actually encode the payload. And it makes sense because if you try typing some emojis, like when I was making this, I was like, hey, let me type in some emoji, and VS Code wouldn't render it. So it's very easy to hide Unicode characters in there, extract the malware, and do evil stuff. And there were a bunch of extensions compromised. And as we can see, OpenVSX had lot many, Microsoft had some, but at the end of the day, a compromise is a compromise. But Glassform wasn't done yet. It was like, you know what? I'm going to come back stronger. So we saw this extension in the wild, and just everybody is familiar with material icon theme. Anybody who has spent time trying to customize Arch Linux knows that we use material icon theme a lot. And they were like, you know what? Icon theme material. It's like they're speaking in Yoda when creating malware, right? And this had something really interesting. This had Glassform version 2 payloads. Now, what does this payload do? First, it checks whether it's activated or not, so it doesn't run multiple copies of itself. If it is activated, it checks, hey, what platform is this? Am I running on Windows? Am I running on Mac? And apparently nobody cares about Linux users because they know they don't have a life. So if they are running on Windows, they will be like, hey, let me load this os.node file. What's a node file, though? We'll come back to it very soon. And if they're running on Mac, they are like, hey, let's load darwin.node. Now, node files is something, they are low-level native binaries. And you have to open it up in IDEA to see what it's doing. So let's just recap what we saw in the last couple of minutes. We had JavaScript. We had JavaScript plus PowerShell. We had JavaScript plus Unicode. And finally, we had JavaScript, and we had to force ourselves to open IDEA. And this thing, when you have to open IDEA during a reverse engineering session, you know you're in time for it's going to be hell, right? So the most powerful thing is going native, which Glassform version 2 did. Why is it more powerful? Because whenever you go native, you can bypass certain restrictions of imposed by Electron, and you can directly interact with OS-level APIs. So let's do that, right? So when we talk about going native, it's one of the reasons or motivations behind going native is that you get to do all the OS level calls. So if you have your sleep mask techniques, you have your ETW patches, and if you want to do something crazy, you can do that, right? And usually, when you talk about extensions, you don't. When you are talking about JavaScript, you don't think about compiled code, right? That's not how usually we think about it. So that also gives you an edge. But the problem was that Electron version 20 did not support FFI. And if you look at the existing FFI libraries, like FFI-RS, which is supported, by the way, they compiled to Node add-ons themselves, like the .node files which we saw. So here was my proposal that, hey, let's cut out the middleman, write our own stuff. And JavaScript does provide the documentation for it. And if you look at the first line of that particular page, it describes Node add-ons as dynamically generated shared objects in C++. The required functions can load them, like when we are using JavaScript, we call the required function. And we can use them on add-ons as well to interact with them, right? From this definition, the one thing which I want to highlight is this dynamically linked shared objects. So essentially, Node add-ons on Windows are DLLs. On Linux, they are shared objects. That's it. It's just a very fancy DLL which knows how to talk to JavaScript. I don't know how to talk to JavaScript, but apparently they do. Nobody knows how to talk to JavaScript. If they say they do, they're lying. But again, coming back to it, let's see how does this whole thing work, right? So whenever you call the required function, if you look at the source code for the loader, you will see it's mapping some things like, say, hey, I have an ID. Why does it map to? Then it checks if this is already loaded or not. But once it sees, OK, this is a .node file, let me call process.dlopen. Process.dlopen tries to call another function called try-load-addon. Try-load-addon calls another process called mplaceback. mplaceback calls a function called dlibopen. dlibopen calls something called uvdlopen. And all of this was to say that it finally calls load library exw. So you take your add-on, it goes through a bunch of JavaScript stuff, and then it finally calls load library exw. For those of you who have been in the Windows malware space, that's how we load a DLL into the existing process. Right, so from there we have the usual kernel 32 call, anti-DLL calls and stuff. So now it's time to weaponize this. Enter the crab man. So why did we choose Rust? This is a question which I've been getting. The official add-on documentation talks about C++, and I believe as civilized people, we don't touch that. And another main reason about why I personally like to avoid C++ is C++ requires a bunch of setup with this tool called Node.js. You have to write a bunch of configuration files, and it's usually a lot more headache to maintain all that. And Rust provides this thing called a Neon RS package manager. Like it's a library built alongside with NPM, so it's very easy. We'll see that in a couple of seconds. And Rust is just better. I can't help that, sorry. But let's see how easy it is to write an add-on using Rust. It's just this. You use npm to initialize a repository. npm creates a repository tree with your usual Rust configuration. And it has a very simple hello world. So the only difference with a traditional Rust program is where we have main. Here we have certain functions which we want to export like a DLL does, and we have to mark it that, hey, this is, with neon export, that, hey, this is a function which is exported to JavaScript, and Rust handles the FFI and everything. And if you look at the contents of package.json, this is really important. One is the main index.node. So it's like specifying the -o flag to GCC. Hey, what do you want the output to be called? Right, we have the build steps, and we can see the first build is done using cargo. And we have the npm build stuff where npm takes that stuff, does its thing to make it compatible with JavaScript. And using add-ons is really simple. You just npm install, npm run build, and you can just call them from your node application. That's it. That's pretty simple. Trust me, I tried with C++. It's not that simple. So now let's put this in a demo extension and try to see how it works. So we install the required dependencies. We use Microsoft's official code generator to create a demo extension. And this is how it looks. It's pretty simple. You have an extension in JS. Now this is the important part, the package.json. The first thing we need to see is the name. This will come in important later. We have the version. We have the engine, which shows which is the minimum version of VS Code which is supported. Activation events. Activation events are something important. How do you trigger an extension? There are a couple of ways. The first way is you call the command itself. Every extension comes with certain commands. You call that, it triggers it. Second are activation events. They are like, whenever, let's say you want to open a certain kind of file, or there are events which trigger a callback and like, hey, this is a Rust file, let me call the LSP server for Rust, or something like that. So it's that sort of stuff. Now this is the main file where the extension commands, like the extension code is there. It's the entry point per se. And this is a command which is registered. Now looking at the source code for the demo extension.js, it's nothing. It has two main functions which we need to take care of. One is the activate function, which is like your main function. This is what is called whenever an extension is triggered. We have the deactivate function when you want the extension to clean up or something like that. And then you just export it. That's how it is. So if we replace our demo hello world add-on with some, let's say we are running some x64 shellcode on here. This is the most classical shellcode execution code right here. And you update the extension.js within the extension itself to include your node add-on and call the function which is called running the shellcode, and you package everything together in a nice little extension and you install it. You should have a shellcode execution. You get your very nice little hello world message box pop-up. But no developer would install this. Hopefully, please. So we need to make it believable that, hey, this is something you need. So the first method is the simplest method, where we yoink the extension code from the open source repositories and stuff. So we will be targeting the same live server Microsoft extension which we saw. It's pretty simple. What we do is we have our malicious add-on. We clone the repository. We put our add-on inside it. And then we need to take care of a few things. Essentially, we need to take care of Webpack, because Webpack, it minifies JavaScript. It bundles everything together, and we don't want Webpack to interfere with our Node add-on. So we just replace our usual required function with non-Webpack required, which just says that, hey, don't touch it. It's all right. I know the guy. That add-on is nice. And then if you have the copy plugin, you just need to update it to add these two lines that, hey, do not touch this file. It is what it is. It's perfect the way it is. So you put everything together, and if you look at the activate function for the live preview Microsoft extension, the only change we need to do here is we need to add these 4 lines where we just declare some stuff. Then instead of requiring it, which we are usually doing, we use the non-Webpack require, and then we call it as usual. Right. And now if we if we package this extension and we install it, we get this. This is a malicious extension. So if we trigger this particular extension, which happens whenever a developer is trying to live preview a HTML file, we'll get a little Cobalt Strike callback while still maintaining the official Microsoft blue tick of trust. Right. So that's scary. But this technique has a few shortcomings. The first thing is, the most important thing is, it still has an IOC. First of all, I don't think anybody here has installed an extension from a VSIX file themselves, right? I think that's a major IOC. Nobody has been in a conversation be like, hey, I installed this VSIX file, you should try that. Nope, doesn't happen. Right. Another thing is the source code does need to be available for this, which is in the case of most extensions, but we are not going to make that assumption. And third is, right at the little corner, it says that, hey, this thing is installed from a VSIX file. So we'll tackle these questions one at a time, starting with what happens when you don't have a source code. So what do we do when we don't have the access to the source code? Let's see that with an example. So this is another extension, does similar things. It is technically also open source, but we don't want to violate any licenses by reverse engineering proprietary products on stage. So that sounds like a disaster. So Microsoft makes these extensions available through an API request. You can call it, save it to disk. Once you have your extension, you can just extract the VSIX, you can unzip it, you can clean up, and you have the extension code. It might be minified code. It doesn't always have to be the source code, but you will have something. And once you have this, what you can do is you can just copy the same malicious payload which you made into the directory. You can update the activate function, put your stuff in there, and then nicely repackage it with a VSIX, like you can zip it again, rename it to a VSIX, and install it using code. And once you do that, you get, again, shellcode execution. Now let's talk about the next thing. How do we make it, like, we get rid of more stuff? And this is a technique which we call fake it till you make it, using that in the industry for a couple of years now. So before that, there are a couple of questions which I want to ask myself. That is, when we are looking at the source code of this particular project, or like any VS Code extension, I did not find any stats. Like, hey, Visual Studio shows you a bunch of stats, the stars, download counts, blah, blah, blah. Where is it getting it from? It was not in the source files. Where is it getting it from? And we saw the IOC where it says it was installed from a VSIX. How is Visual Studio Code determining that? So turns out if you look at the source code, it has a class which has a bunch of functions, which makes a bunch of API requests, it gets the data, blah, blah, blah. Too much jargon. Let's see that in action. Very simple. Remember we talked about the extensions.json file, which is in the home of the extension folder? Let's take a look at its contents, right? We installed the VS Code Live server, and now let's just take a look. First thing is the identifier. The identifier is made out of 2 parts. The first part is the publisher, which is MS VS Code. Second part is the .live server, the name of the extension. It has the version information. It has a path to where the extension is stored on disk. And it has a source. It says gallery. Whenever the source is gallery, it means it's installed from the marketplace, right? So let's see what the API request is. And whenever you load an extension, VS Code makes this API request and stuff. But the thing to note here is, this is the only parameter which it sends. No signatures, nothing. It just takes the ID from the previous step, right? That's it. And if you look at the response, it might be a bit hard to follow. I didn't. OK, so the response to this particular API request, where we just need to control the ID parameter, is a bunch of information about the extension itself. The one to note here is domain verified true? I'm assuming this is the one due to which we get the blue tick of approval. We have the extension name, the display name. We have the version information. We have a bunch of flags which might be useful. We have asset URIs. We have the stats. So this is where they are getting the stats from, right? So let's install a demo extension and check how does the extension.json look. Right? We just create a demo extension, does nothing, and we just examine the extensions.json again. We see that for our extension, which is the most run out of the box extension, it has the identifier as undefined publisher.demo extension. So naturally, when the API makes a request with this ID, it doesn't get back anything. And it says right at the end, the source is VSIX. So at this point, the question is, if we control the environment in any way, can we not just update these parameters ourselves in extensions.json? Let's say I put a normal dummy extension, and then what it does, it makes some changes to extensions.json and says that, hey, my ID isn't unpublished dot anything. My ID is msvscode.live server. I can just say who I am. So that's what we do. We write a little JavaScript, unfortunately. Nobody should do that. Where we import some stuff. We write a function which updates the extension. These are targets. We want to pretend that we are Microsoft's live server. We read our package.json. We get the inputs we want. We also read the the unmodified extensions.json and get the inputs we want. And then we make the API request with the ID. We read the response, update the fields. And finally, we write our extension, we update the file paths and update the extensions.json. So let's see a demo. Oops. It's OK. So here is the extension stuff. And we packaged it up. We installed our demo extension, which is ugly. If you go there, we see this, and they're like, hey, this is a bad extension. And the source still says it's a VSIX one. It runs it, and what we did right now, we ran the demo extension and it updated the extensions.json file. So while this is me fumbling to find the right keys. And if we make this full screen, please. Now it reads as live preview. You can also update the README and a bunch of stuff. This is not the best OPSEC, but you get the idea. You can just close. So now what you can do is you can just pretend that, hey, this is live preview. But there's so many more ideas with this, right? You can definitely spoof extensions. What you can do is you can write some better code, and you can maybe drop your payloads right. Let's say there is a Cloud Code extensions installed in multiple PCs of multiple developers. You can just insert it there. You can also have a non-malicious extension published, and then when you want to maybe run a test on something, you auto-update it with some code like we see in the wild. So the possibilities are limitless. These are just few examples which I brought up. So how do you detect this? First, obviously, be aware of typo squatting attacks, mismatching names and stuff. A very big IOC is loading a .NOTE file because you don't usually find .NOTE files in the wild, especially not in an extension. Again, installing directly from VSIX files is also a red flag. And every detections which you would apply to a normal DLL, they would also apply here. Because again, these are DLLs by nature. You can prevent these by restricting certain command line flags to load them from disk. You can do a signature check that, hey, is this extension has been modified in some way or not? You can have, as an organization, have a well-audited list of extensions, and finally maintain a software bill of material so that you know what things are running on your system. Right. But what are the future plans with this? This technique does not end here. If anything, we have seen more extension stuff coming out in the recent years with other software. Right. MCP servers are coming out. Like Cloud desktop apps, they follow a very similar structure to VSIX files. So what you can do is you can maybe take some components of this particular thing, especially with the add-on stuff. You can slap it on top of a VSIX file and then distribute it to gain initial access in environments where you have certain whitelisting and stuff. Because with AI coming in so hot, a lot of organizations which I've seen in my professional experience, they whitelist AI. They're like, okay, Claude is doing things, don't look at it. So that's a really interesting attack vector which I would love to talk about or explore and stuff. And you can put it in an MCP server and just profit and yeah, just get your shells. But that's it. That's the end of my talk. Thank you everyone for attending. And yeah, do check us out.
Woohoo! Woo! Nice.
All right.
Thank you, DB.
Thank you so much.
Any questions?
We've got a mic.
Why are you
Jesper
so
with a mic.
afraid? I have a mic. Questions?
Any hands?
No?
All right.
This is what I talked about yesterday.
Yeah.
Be ready for the storm.
Oh, we got one over here.
We did? One brave soul. Can we do a, can you help me? Thanks. Or maybe I didn't put it on.
And then pass it back when you ask.
I was wondering, have you looked at the security implications or boundaries between the extensions that you can run in a dev container versus in the main VS Code process?
See, the dev containers of Electron, right? Like VS Code is an Electron app. So previously we used to do that, but when you talk about containers, they restrict your access to OS level APIs and stuff. This is what actually happened in Electron 21 and stuff. Before Electron 21, it was FFI. You can run things willy-nilly. But what Electron 21 was like, hey, you can only work with memory within certain offsets. These are memory cages and stuff. So we had that. We did that before Electron started doing stuff. But one, if you look at it right now, if you want to work with pure JavaScript, you cannot do that anymore. If you cannot get access to OS level APIs from JavaScript, you have to use an add-on. I forgot the name of the exact FFI library which JavaScript was using. That doesn't work whenever you try to package it in Electron. So whatever works, for example, FFI-RS is one thing which works when you're talking about FFI. You might be thinking that, okay, this is JavaScript code, but if you take it apart, it is, again, an add-on. So at that point, it's like, as malware developers, it's very important to have low-level access of stuff to do API things. So I think instead of taking the long way where you write JavaScript code, which compiles into Node, which does your stuff, directly write a Node file. And also, like, another reason why we prefer Rust here is, if you look at existing tradecraft, if you look at the things which, for example, Malware Academy produces and stuff, a lot of those POCs are already in Rust. Right, so it's very easy. It's easier to translate them into working proof of concepts, which you can ship out during your engagements, and instead of going the JavaScript way.
Okay.
I think that's all we have time for. Thank you again so much.